Tonight, we're going to explore one of the most baffling encounters in the history of astronomy. An object appeared in our solar system from the depths of interstellar space. It wasn't a comet. It wasn't an asteroid. It didn't match anything astronomers had ever seen before. It moved through our cosmic neighborhood at a speed so extreme that the sun's gravity couldn't hold onto it. And then, before scientists could properly study it, it vanished back into the darkness between the stars, taking its secrets with it. The object was less than a quarter-mile long. It tumbled chaotically as it traveled. It accelerated in ways that violated the laws of physics as we understand them for natural bodies. Its shape, if our best models are correct, was unlike anything that had ever been observed in space. Some respected scientists, including the chair of Harvard's astronomy department, openly suggested it might not be natural at all, that it might be artificial, that it might be a piece of alien technology drifting through our solar system after a journey that lasted millions, perhaps billions of years. By the end of tonight, you're going to understand exactly what happened during those 11 days in October and November 2017, when humanity got its first close look at a visitor from another star system. You'll learn why nearly a decade later, despite the most sophisticated telescopes on Earth and in space turning their attention toward it, scientists still cannot agree on what it was. And you'll discover why this single object forced astronomers to reconsider some of their most basic assumptions about what's possible in our galaxy. Before we get started, if you love exploring the mysteries of the cosmos as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The date is October 19, 2017. Robert Werrick, a postdoctoral researcher at the University of Hawaii's Institute for Astronomy, is reviewing data from the Pan-SDARS-1 telescope on Haleakala, the dormant volcano on the island of Maui. Pan-SDARS is one of the most sensitive sky survey instruments ever built. Its 1.8-meter telescope photographs the entire visible sky every few nights, looking for anything that moves against the background of stars, asteroids, comets, near-Earth objects that might one day threaten our planet. On this particular night, Werrick notices something unusual, a faint object moving across the sky in a way that doesn't quite match anything in the catalogue. He calculates its trajectory. He runs the numbers again. He gets the same answer. He runs them a third time with different software. The answer doesn't change. Whatever this object is, it cannot be from our solar system. Its orbit is hyperbolic, meaning it's moving so fast that the sun's gravity will never be able to capture it. It came from somewhere else. It's only passing through. This is unprecedented. In over 2 centuries of systematic astronomical observation, no one has ever conclusively detected an object that came from outside our solar system. There have been hints. There have been suspicious orbits. But every previous candidate had eventually been explained as a comet from the distant Oort cloud, perturbed by passing stars, with an orbit that only seemed interstellar. This was different. This object was moving at 196,000 miles per hour relative to the Sun, far faster than any solar system object could possibly travel without being ejected entirely. It wasn't going to slow down. It wasn't going to be captured. It was just visiting. Werrick alerts his colleagues. Within hours, the Minor Planet Center in Cambridge, Massachusetts, issues an electronic circular to the world's astronomical community. Telescopes around the world begin turning toward the object's calculated position. They have to act fast. The object is already on its outbound trajectory. It had passed its closest approach to the Sun back on September 9, just 6 weeks earlier. Now it's racing away, growing fainter every night as the distance increases. There are perhaps a few weeks at most before it becomes too dim to observe even with the largest telescopes on Earth. The astronomical community names it 1I2017U1. The 1I designation is historic. It's a new classification. The I stands for interstellar. This is the first object ever assigned to this category. There has never been a need for the category before. The Hawaiian discoverers also give it a name that reflects its origin and the place where it was found. They call it Oumuamua. In the Hawaiian language, the word roughly translates to scout or messenger from afar arriving first. More poetically, a messenger sent from the distant past to reach out to us. The name fits, because as observations pour in from telescopes across the world, Oumuamua starts behaving in ways that no one expected. The first surprise comes from its brightness. Astronomers can estimate the size of distant objects by measuring how much light they reflect. Oumuamua is small, perhaps 100 to 200 meters in length, about the size of a skyscraper laid on its side. That's not particularly unusual for a small asteroid. What's unusual is how its brightness changes over time. Most asteroids rotate, and as they rotate, their brightness varies. An elongated asteroid appears brighter when its long side faces Earth and dimmer when its narrow end points toward us. The amount of brightness variation gives astronomers a clue about the object's shape. A typical asteroid varies by a factor of 2 or 3. Oumuamua varied by a factor of 10. That's extreme. That's the most extreme variation ever observed in a solar system object. It means Oumuamua wasn't just elongated. It was wildly elongated. The most likely explanation is that it was at least 10 times longer than it was wide. Possibly more. Try to picture that. Imagine an object roughly the proportions of a cigar or perhaps a pancake. Either way, something dramatically different from the lumpy potato shapes of most asteroids. No object of that shape had ever been observed in our solar system. Asteroids and comets tend to be roughly spherical or irregularly clumped because their formation processes don't favor extreme elongation. Even fragments from collisions usually end up with more equal dimensions. Oumuamua was an outlier so extreme that some scientists initially questioned whether the brightness measurements were correct. But the measurements were confirmed by multiple independent observatories. The shape was real. Then came the second surprise. Astronomers had assumed Oumuamua would behave like a comet. Comets are icy bodies that, when they approach the sun, release gas and dust as their ices vaporize. This creates the visible tail and the fuzzy coma surrounding the nucleus. The released gas also produces a small but measurable thrust, slightly altering the comet's trajectory. It's called non-gravitational acceleration, and it's a signature feature of cometary activity. The expectation was straightforward. Oumuamua had passed within 24 million miles of the Sun, closer than Mercury's orbit. Whatever ices were on its surface should have vaporized intensely. There should be a tail. There should be a visible coma. There should be all the classical signs of cometary activity. There were none, not a wisp, not a trace. Despite the most sensitive observations astronomers could deploy, including images from the Hubble Space Telescope, no cometary activity was detected. No outgassing visible, no dust trail, no coma. By every visible measure, Oumuamua appeared to be a bare rock, an asteroid, not a comet, except for one thing. As astronomers tracked its outbound trajectory with increasing precision, they realized Oumuamua wasn't quite following the path it should have been following. The sun's gravity should have decelerated it by a precisely calculable amount. Instead, the object was traveling slightly faster than gravity alone could explain. Something was giving it an extra push, a tiny but measurable acceleration directed away from the sun. This was strange. This was the kind of acceleration you'd expect from a comet's outgassing, but there was no visible outgassing. The acceleration was there, but the cause was invisible. Marco Micheli, an astronomer at the European Space Agency, led the team that confirmed this anomalous acceleration. They ruled out every conventional explanation they could think of. It wasn't an error in measurement. It wasn't gravitational influence from a hidden body. It wasn't radiation pressure from the sun, at least not at the magnitudes typical for solid asteroids. The acceleration was real, it was measurable, and it had no obvious cause. This is where Oumuamua transitioned from being a fascinating curiosity into being a genuine scientific puzzle. An object that looked like an asteroid, but accelerated like a comet without showing any signs of cometary activity. An object shaped like nothing ever seen before. An object moving on a trajectory that proved beyond any doubt it had come from outside our solar system. And humanity had only a few weeks to study it before it faded back into the darkness from which it came. Telescopes around the world worked frantically. The European Southern Observatory's Very Large Telescope in Chile, the Gemini South Telescope, the Keck Observatory in Hawaii, the Hubble Space Telescope, the Spitzer Space Telescope. Every major instrument capable of detecting the faint object turned to look. They gathered every photon they could. They measured its spectrum, its rotation, its color, its motion. They tried to determine its composition. They tried to understand what they were seeing, but the window was closing fast. By December 2017, Oumuamua was already too distant for spectroscopy. By January 2018, only the largest telescopes could detect it at all. By June 2018, even the Hubble Space Telescope, humanity's most sensitive observatory, lost the object entirely. It had become too faint to see. It continues outbound to this day, racing toward the constellation Pegasus at over 58,000 miles per hour relative to the Sun. It will never return. It will never be observed again. Everything we know about it, and everything we will ever know, comes from those few weeks of frantic observation in late 2017 and early 2018. And what those observations revealed was a mystery that scientists, despite nearly a decade of analysis and debate, still cannot explain. To understand why Oumuamua became such a profound scientific puzzle, we have to understand what astronomers expected to find when they finally detected an interstellar object, because they had been expecting one for decades. They just didn't know when it would arrive or what it would look like. The expectation came from a simple mathematical argument. Stars form in clusters, and as planetary systems develop, they eject material. Comets and asteroids that get gravitationally slung too hard by passing planets end up on hyperbolic trajectories. They escape their parent star and drift into interstellar space. Our own solar system has done this. During the early chaotic period, when the giant planets were migrating to their current orbits, billions, perhaps trillions of icy objects were ejected from our system into the galaxy. Every other planetary system probably did the same thing. Over billions of years, the galaxy should be filled with these ejected objects, drifting between the stars. Eventually, some of them should pass close enough to our solar system to be detected. The math suggested it should happen reasonably often. Calculations from the 1970s and 80s estimated that there might be one interstellar object per cubic astronomical unit at any given time within the inner solar system. The reason no one had detected one before wasn't because they didn't exist. It was because we didn't have sensitive enough telescopes to find them. PAN-SDARS changed that. Operating since 2010, it was specifically designed to catch faint moving objects. By 2017, it had been scanning the sky systematically for 7 years. Astronomers had been waiting. They knew that statistically, an interstellar object should be detected eventually. They knew what it should look like. And then Oumuamua appeared, and almost nothing about it matched expectations. Here's what astronomers expected an interstellar object to be. It should be a comet. The reasoning was straightforward. Comets contain ices that survive for billions of years in the cold of interstellar space, because temperatures there are only a few degrees above absolute zero. Asteroids, on the other hand, are rocky and metallic. The interior of a planetary system that has lost its star, drifting through interstellar space, should be biased toward producing icy ejected bodies because the outer regions of planetary systems contain far more material than the inner regions, and that outer material is icy. When this hypothetical interstellar object passed close to our Sun, the ices should vaporize, producing the classic comet appearance. A glowing coma, a trailing tail. Spectral signatures of water, carbon dioxide, carbon monoxide, methane, the same compounds found in comets that originated in our own solar system. Oumuamua showed none of these signatures. Its spectrum was reddish, similar to certain types of asteroids found in the outer solar system. It had no visible coma. It had no tail. It produced no detectable gas. The most sensitive searches found upper limits on the amount of water being released, and those upper limits were extraordinarily low. If Oumuamua was outgassing water, it was doing so at a rate of less than a few tenths of a kilogram per second. For comparison, a typical comet releases tons of water per second when near the Sun. This created the first major mystery. Oumuamua had to be outgassing something because of the anomalous acceleration, but it wasn't outgassing water. It wasn't outgassing carbon dioxide. It wasn't outgassing carbon monoxide. The standard cometary ices were all ruled out by spectroscopic observations. So what was producing the acceleration? The acceleration itself was tiny but unmistakable. The team led by Marco Micheli published their analysis in the journal Nature in June 2018. They had tracked Oumuamua's position with extraordinary precision using observations from multiple telescopes. They had modeled every possible gravitational influence. They had accounted for the gravitational pull of every planet, every major moon, every large asteroid. They had even accounted for the relativistic effects predicted by Einstein's general theory of relativity. After all these corrections, there remained a residual acceleration that pointed directly away from the Sun and decreased with distance from the Sun in a specific way. This is the signature of cometary outgassing. Material vaporizes on the sunward side of the nucleus and creates a jet of gas pointing toward the Sun. Newton's third law produces an equal and opposite reaction, pushing the nucleus slightly away from the Sun. The magnitude depends on how much material is being released and how quickly. The dependence on distance from the Sun matches what you'd expect from solar heating driving the vaporization. Oumuamua's acceleration matched this signature perfectly in direction and distance dependence, but the magnitude was strange. For an object of Oumuamua's size, the acceleration was larger than expected for any plausible amount of normal cometary outgassing. And again, there was no visible outgassing. Whatever was producing the acceleration was completely invisible to the most sensitive instruments humanity could deploy. Several explanations were proposed. The first was that Oumuamua was outgassing hydrogen. Pure molecular hydrogen is essentially invisible to spectroscopy at the wavelengths astronomers were using. It could be released in significant quantities without being detected. The proposal was that Oumuamua might be a hydrogen iceberg, a chunk of frozen molecular hydrogen formed in an extremely cold molecular cloud. As it approached the Sun, the hydrogen would sublimate, producing the observed acceleration while remaining invisible. The problem with this theory is that hydrogen icebergs may not be able to form in the first place. Molecular hydrogen requires temperatures below about 3 Kelvin to remain solid, which is colder than the typical interstellar medium. Even in the coldest molecular clouds, temperatures are usually closer to 10 Kelvin. And even if a hydrogen iceberg could form somewhere, it would have evaporated during its long journey through the galaxy. Cosmic rays alone would deposit enough energy to warm it past the sublimation point over the billions of years required to travel between stars. A second theory proposed that Oumuamua was outgassing nitrogen, specifically that it was a fragment of a nitrogen ice-covered planet, similar to Pluto or Triton. A massive collision in some distant solar system could have shattered such a world, ejecting fragments into interstellar space. One of those fragments, after a long journey, happened to encounter our solar system. The nitrogen ice would sublimate near the Sun, producing acceleration without being easily detected, since nitrogen has very weak spectral features in the wavelengths astronomers typically observe. This theory has more physical plausibility than the hydrogen iceberg model. Nitrogen ice is stable at temperatures that exist in the outer regions of planetary systems. Triton has surface temperatures around 38 Kelvin, and its nitrogen ice has been stable for billions of years. A fragment shielded by its own outer layers could potentially survive interstellar transit, but it requires a very specific origin scenario, a collision sufficient to shatter a Pluto-like body, but not so violent that it would have destroyed the fragment we observed. And it requires that fragment to have made the journey to our solar system within the lifetime of our observational capabilities, which seems statistically unlikely. A third theory was even stranger. It came from Avi Loeb, the chair of the astronomy department at Harvard University, one of the most respected institutions in the world. Loeb had been involved in the Breakthrough Starshot project, an initiative to develop technology that could send tiny probes to nearby stars using light sails. He noticed something about Oumuamua that the data seemed to support, but most astronomers were reluctant to consider. Oumuamua's acceleration without visible outgassing could be explained naturally if the object had an extremely high surface area relative to its mass. A light sail, for instance, would experience exactly the kind of radiation pressure from sunlight that Oumuamua appeared to be experiencing. Solar photons striking a reflective surface push that surface outward. For a thin, flat object, this force could be substantial. Light sails work on exactly this principle, and several space missions had already tested the concept. Loeb's calculations suggested that Oumuamua could be explained as a light sail if it was extremely thin, perhaps less than a millimeter thick, and had high reflectivity. The shape would need to be flat rather than cigar-shaped, more like a pancake or a sheet. Interestingly, when astronomers reanalyzed Oumuamua's brightness variations, the pancake shape actually fit the data better than the cigar shape. Both shapes could explain the tenfold brightness variation, but a flat, disk-like geometry was statistically favored. Loeb co-authored a paper with his postdoctoral researcher S.H. Mule Bialy proposing that Oumuamua might be artificial. Specifically, that it might be a piece of alien technology, possibly a defunct light sail from some distant civilization, drifting through the galaxy after its mission was completed millions or billions of years ago. The paper appeared in the Astrophysical Journal Letters in November 2018, just over a year after Oumuamua's discovery. The scientific community's reaction was mixed. Most astronomers found the alien technology hypothesis deeply uncomfortable. Extraordinary claims require extraordinary evidence, the old saying goes, and proposing alien artifacts is about as extraordinary as a claim can get. Many critics argue that natural explanations, even unlikely ones, should be preferred over invoking alien intelligence. The principle of parsimony, often called Occam's razor, suggests choosing the explanation that requires the fewest unsupported assumptions. Loeb's response was characteristically direct. He argued that all the proposed natural explanations were themselves extraordinary. A hydrogen iceberg that shouldn't be able to form, a nitrogen fragment from a specific type of collision, a shape unlike anything previously observed, behavior that didn't match any known class of solar system object. At what point, Loeb asked, does insisting on natural explanations become more strained than considering artificial ones? The debate became surprisingly bitter. Some of Loeb's colleagues accused him of seeking publicity. Others defended his right to propose any hypothesis the data could support. The scientific community is supposed to be open to new ideas, the defenders argued. If a respected astronomer at Harvard cannot openly discuss the possibility that an anomalous object might be artificial, then science has failed in its commitment to follow evidence wherever it leads. The argument continues to this day. Loeb has expanded his hypothesis in subsequent papers and a popular book titled Extraterrestrial, published in 2021. Other scientists have continued to develop natural explanations. A 2023 paper proposed that Oumuamua might be a hydrogen-rich fragment of a primordial planetesimal, with hydrogen trapped in water ice rather than existing as pure hydrogen ice. Another paper suggested it might be a chunk of organic-rich material with unusual surface chemistry. Every few years, a new theory appears, attempting to explain the anomalies without invoking alien technology. None of these theories has gained universal acceptance. Each one requires specific assumptions about composition or formation history. Each one has problems, and none of them can be tested because Oumuamua is gone, racing away from our solar system at tens of thousands of miles per hour, never to return. What we have is a handful of observations from a few weeks in late 2017. A spectrum showing reddish color, a rotation period of about 8 hours, but with chaotic tumbling rather than smooth spin, a size estimate of around 100 to 200 meters, a shape that was extremely elongated, possibly flat, an acceleration that pointed away from the sun, no visible outgassing, no detectable composition, a trajectory that proved it came from interstellar space, and then darkness. The chaotic tumbling of Oumuamua deserves special attention because it tells us something important about the object's history. Most asteroids and comets in our solar system rotate smoothly around a single axis. They spin like a top, with their rotation stabilized by the conservation of angular momentum and by the way mass is distributed throughout their bodies. Some objects do tumble, rotating around multiple axes simultaneously in a chaotic motion, but tumblers are relatively rare and usually have specific origins, like recent collisions that knock them off their stable rotation. Oumuamua was not rotating smoothly. Its brightness variations didn't follow a simple repeating pattern. Instead, they showed the complex signature of an object tumbling end over end while also spinning around its long axis, with the two motions combining into a chaotic dance that took about 8 hours to roughly repeat. Some analyses suggested the tumbling motion had been stable for at least 1 billion years, perhaps much longer. This is significant because it tells us Oumuamua had been damaged at some point. Something had struck it hard enough to knock it off its stable rotation. The original event could have happened recently in cosmic terms, perhaps within the last few 100 million years, or it could have happened in the distant past, with the object slowly tumbling through interstellar space for billions of years afterward. The mathematics of rotational damping in airless bodies suggests tumbling motions slowly damp out over time. But for an object as small as Oumuamua, the damping timescale could exceed the age of the universe. So the chaotic rotation could be ancient. Whatever knocked Oumuamua into its tumbling state must have been significant. A grazing impact from another object. A catastrophic collision that broke off this fragment from a larger parent body. Some violent gravitational interaction during ejection from its home solar system. Whatever the cause, Oumuamua bears the scars of cosmic violence. This is consistent with the natural origin hypothesis. Fragments of larger bodies, ejected violently from their parent systems, would naturally end up tumbling chaotically. Asteroids in our own solar system that have suffered recent impacts often show similar chaotic rotations. But it doesn't rule out the artificial hypothesis either. A defunct piece of technology, perhaps damaged by micrometeorite impacts over millions of years in interstellar space, could also end up tumbling chaotically. The tumbling motion also helps explain why measuring Oumuamua's exact shape was so difficult. With a smoothly rotating object, brightness variations directly trace the projected cross-section as the object spins. With a tumbling object, the brightness changes reflect both shape and the changing orientation. Disentangling these effects requires assumptions about the rotation, and different assumptions lead to different shape models. This is part of why the cigar shape and the pancake shape both remain plausible interpretations of the same brightness data. Color is another piece of the puzzle. Oumuamua appeared reddish in observations across multiple wavelengths. The reddish tint is similar to certain types of asteroids found in the outer solar system, particularly objects in the Kuiper belt and among the centaurs that orbit between Jupiter and Neptune. These bodies acquire their red color through long exposure to cosmic radiation. Organic molecules on their surfaces gradually break down and recombine into complex compounds called tholins, which appear red or reddish-brown. This is the same process that gives Pluto and some of its moons their reddish coloration. If Oumuamua's color comes from tholins, it suggests prolonged exposure to cosmic radiation. This fits with an interstellar origin. An object drifting through the galaxy for millions or billions of years would accumulate exactly this kind of surface chemistry. Cosmic rays would slowly process any organic compounds on its surface, producing the characteristic red coloration. The color tells us Oumuamua had a long journey through interstellar space, which is consistent with both the natural and artificial hypotheses. The color also tells us something else. Oumuamua probably had a dark surface, similar to the surfaces of asteroids that have been weathered by space. This dark surface absorbs most of the sunlight that hits it. The small fraction of light reflected back is what we observed from Earth. A dark surface argues against some versions of the artificial hypothesis. A pristine alien light sail would presumably be designed to be highly reflective, since that's the entire point of a light sail. Why would alien engineers build a sail that absorbed most of the light it encountered? On the other hand, A sail that had been drifting through space for millions of years would gradually accumulate dust and become darker, regardless of its original design. Now we need to think carefully about where Oumuamua came from. Its trajectory through our solar system allows astronomers to trace its path backward through space, calculating where it came from and how it got here. The results are intriguing. Before entering our solar system, Oumuamua was moving relative to the local standard of rest. This is the average motion of all the stars in our galactic neighborhood, calculated by averaging out individual stellar motions. The local standard of rest is a useful reference frame because objects that have been drifting through interstellar space for a very long time tend to settle into motion close to this average. The longer an object has been wandering, the closer its velocity tends to be to the local standard of rest. Oumuamua's velocity was remarkably close to the local standard of rest, closer than the velocity of any nearby star. This is unusual. Stars typically have peculiar velocities of tens of kilometers per second relative to the local standard of rest, the result of their formation conditions and gravitational encounters over their lifetimes. Oumuamua had a peculiar velocity of only about 10 kilometers per second, much smaller than most stars. This could mean Oumuamua had been drifting for a very long time, gradually settling into motion close to the galactic average. Or it could mean it originated from a relatively young population of stars whose own velocities are close to the local standard of rest. Either interpretation pushes the origin into deep time or specific environmental conditions. Astronomers tried to identify possible parent stars for Oumuamua. The basic approach involves calculating its trajectory backward and seeing which stars were near that path in the past. Several candidates were proposed. A team led by Baylor Jones at the Max Planck Institute for Astronomy examined the Gaia Space Telescope's catalogue of stellar motions, looking for stars that Oumuamua might have passed close to in the recent astronomical past. They found several candidates, but none was definitively identified as the parent system. The closest encounters happened millions of years ago, with stars hundreds of thousands of astronomical units away at the time of closest approach. Those distances are too large to confidently identify any specific star as Oumuamua's home. This is partly because we don't know precisely how Oumuamua was traveling before it entered our solar system. We measured its trajectory only after solar gravity had already started bending its path. Working backward through that bending process introduces small uncertainties that grow rapidly when extrapolated over millions of years. After perhaps 10 or 20 million years, the uncertainty in Oumuamua's prior position becomes larger than the typical distance between stars. We simply can't trace its origin with the precision needed to identify a specific source. This is frustrating, but important to understand. Oumuamua's origin is genuinely unknown. It came from somewhere in the direction of the constellation Lyra, and it had been traveling for at least millions of years, probably much longer. Beyond that, we cannot say. Its home star, if it had one, might be a star we've catalogued or a star we haven't yet observed. It might still exist. It might have died long ago, leaving only a white dwarf or neutron star or black hole behind. The journey Oumuamua took to reach us was almost unimaginable in scope. Even at typical interstellar object speeds, traveling between stars takes millions of years. The nearest stars are several light years away, and Oumuamua wasn't traveling at light speed. It was moving at perhaps 20 kilometers per second relative to the local standard of rest, which is fast by human standards but glacial compared to light. At that speed, crossing one light year takes about 15,000 years. Crossing from a nearby star system to ours would take hundreds of thousands of years at minimum, more likely millions. During those millions of years, Oumuamua was utterly alone. The interstellar medium is so empty that the object would rarely have encountered anything. The occasional cosmic ray would strike it. Very rarely it might pass through a dust cloud. Even more rarely, it might have a close encounter with a star. Most of the time, it just drifted through near-perfect vacuum, in near-perfect cold, in near-perfect darkness, year after year, century after century, millennium after millennium. The temperature in interstellar space is only about 3 degrees above absolute zero, the residual heat from the Big Bang itself. At those temperatures, almost everything is frozen solid. Even helium becomes liquid at temperatures around 4 Kelvin. The chemistry of interstellar space is dominated by the slow processing of materials by cosmic rays rather than by thermal reactions. Surface chemistry happens, but extraordinarily slowly. The reddening of Oumuamua's surface that we observed would have taken millions of years to develop fully. Eventually, Oumuamua entered the gravitational influence of our solar system. This would have happened slowly, with the sun's gravity gradually beginning to deflect its trajectory. The deflection would have been small at first, becoming more pronounced as the object approached. By the time Oumuamua was within Jupiter's orbit, the sun's gravity was bending its path significantly. By the time it was within a few astronomical units of the sun, its trajectory was being shaped almost entirely by solar gravity. The hyperbolic shape of its orbit is what proves Oumuamua came from interstellar space. Hyperbolic orbits represent paths that pass once near the sun and then escape forever. They're the trajectories of objects moving too fast for the sun to capture. Comets in our own solar system follow elongated elliptical orbits, returning periodically to the inner solar system. Even comets from the distant Oort cloud, with orbital periods of millions of years, are still gravitationally bound. They will return eventually. Hyperbolic orbits never return. They pass through once, and they're gone. Oumuamua's orbit was unambiguously hyperbolic. Its eccentricity, the parameter that describes how much an orbit deviates from a perfect circle, was 1.2. Eccentricities below 1 describe bound elliptical orbits. Eccentricities above 1 describe unbound hyperbolic orbits. An eccentricity of 1.2 is well above the threshold. There was no doubt. Oumuamua came from elsewhere and was leaving forever. The closest approach to the Sun happened on September 9, 2017. At that point, Oumuamua was about 24 million miles from the Sun, between the orbits of Mercury and Venus. Intense solar heating during this perihelion passage is what should have triggered any cometary activity. The fact that no such activity was observed is one of the central mysteries of the encounter. Whatever Oumuamua was made of, it did not vaporize visibly even at that proximity to a star. After perihelion, Oumuamua began racing outward. By the time it was discovered on October 19, it had already crossed Earth's orbit and was heading toward the asteroid belt and beyond. Astronomers had missed the closest approach entirely. The object had been too close to the sun in the sky to be observable during its sunward passage. Only after it had moved into the night sky on its outbound leg did PANSTARRS catch sight of it. This is part of why studying interstellar objects is so difficult. They appear without warning, race through the inner solar system, and disappear before we can mount any meaningful response. The frantic observation campaign that followed Oumuamua's discovery deserves to be understood in detail, because it reveals both the incredible capabilities of modern astronomy and its limitations. When word went out through the Minor Planet Center on October 25, 2017, that an unusual object had been detected on a clearly hyperbolic trajectory, the response was immediate and global. Telescopes that had been scheduled for other observations were rapidly reassigned. Astronomers who had been working on completely different projects dropped what they were doing. The interstellar object had been predicted for decades, and now it was here, but it wouldn't stay long. The first follow-up observations came from the European Southern Observatory's Very Large Telescope in Chile. This complex includes 4 8-meter telescopes that can work independently or be combined into an interferometer with the resolving power of an effective 16-meter telescope. The VLT observations on October 25 and 26 confirmed the object's brightness variations and provided the first detailed spectroscopic measurements. The spectrum showed the reddish color that suggested an outer solar system origin, but it lacked the specific spectral features that would have indicated water ice or other common cometary materials. Karen Meech, the astronomer who led the international observation campaign, described the moment when the brightness variations were first confirmed as profoundly strange. The team had expected something unusual, but the magnitude of variation was beyond anything in their experience. Asteroids that vary by a factor of 2 were considered elongated, A factor of 3 was extreme. Oumuamua varied by a factor of 10 and possibly more. Some measurements suggested variations as large as a factor of 15, though the exact value depended on assumptions about the rotation. Whatever shape this object had, it was unlike anything in the catalogue of known solar system bodies. Within days, observations were pouring in from telescopes around the world. The Canada-France-Hawaii telescope on Mauna Kea, the Gemini telescopes in both hemispheres, the Magellan telescopes in Chile, the Nordic Optical Telescope in the Canary Islands, the William Herschel telescope, the Discovery Channel telescope in Arizona, the Cala Alto Observatory in Spain. Every major facility capable of observing the rapidly fading object turned to look. The Hubble Space Telescope was tasked with the most precise positional measurements. Hubble's location above Earth's atmosphere gives it a tremendous advantage for measuring the exact positions of faint objects. The atmosphere blurs and shifts the apparent positions of celestial objects in ways that can introduce small errors. From space, no such errors exist. Hubble's measurements of Oumuamua's position allowed astronomers to trace its trajectory with extraordinary precision, which is how the anomalous acceleration was eventually detected. The Spitzer Space Telescope, an infrared observatory, attempted to detect heat emission from Oumuamua. If the object had any thermal signature different from solar reflection, Spitzer should have been able to detect it. The observations placed strict upper limits on any thermal emission, which in turn constrained the object's size and reflectivity. The size estimates of 100 to 200 meters came partly from combining the brightness measurements with the upper limits from Spitzer. What no telescope could detect was any sign of cometary outgassing. The most sensitive searches looked for emission from carbon-bearing molecules, particularly cyanide, which produces strong emission lines and is one of the most easily detected molecules in cometary comas. There was nothing. They looked for water emission. Nothing. They looked for dust. Nothing. They looked for any of the typical signatures of cometary activity, and they found absolutely none. This was so unusual that some scientists initially proposed Oumuamua might be in a state called dormancy. Some comets in our solar system go through dormant phases where their surfaces become covered with a layer of refractory material that suppresses outgassing. The comet Halley showed this behavior in some respects. Perhaps Oumuamua had spent so long in interstellar space that any volatile materials on its surface had been buried under a layer of inactive crust. The inner parts might still contain ices, but they would be sealed away from sunlight. The problem with the dormancy hypothesis is the anomalous acceleration. If Oumuamua was completely dormant, what was producing the acceleration? Something was pushing it outward. Whatever that something was, it had to be invisible to all our instruments, and yet powerful enough to measurably affect the object's trajectory. The combination of no visible outgassing and clear non-gravitational acceleration was unprecedented. Other theories emerged as the data accumulated. One proposal was that Oumuamua might be an extinct comet nucleus, a body that had once contained ices but had exhausted them all during previous close encounters with stars. The acceleration could then come from solar radiation pressure on a very low-density body. This requires Oumuamua to be remarkably porous, almost like a cosmic dust bunny held together by weak Van der Waals forces. The density would need to be perhaps 1/10 that of water, much less than any known asteroid or comet. This porosity hypothesis has some appeal. Recent studies of cometary nuclei from missions like Rosetta showed that comets can have surprisingly low densities, suggesting they're held together loosely rather than being solid rock or ice. If interstellar wandering somehow produced even more porous bodies, perhaps through long exposure to cosmic rays gradually disrupting the internal structure, then Oumuamua might fit. But this requires a porosity beyond anything previously observed, and it doesn't explain why no outgassing was detected during the close solar approach. The observation campaign also tried to determine Oumuamua's composition more precisely. Different materials reflect light in different ways across the spectrum, from ultraviolet to infrared. By measuring the reflected light at many wavelengths, astronomers can sometimes determine the surface composition without needing direct samples. For Oumuamua, the spectrum was relatively featureless. It didn't show the specific absorption bands that would indicate water ice, methane ice, or other identifiable compounds. It looked similar to certain types of asteroids called D-type asteroids, which are common in the outer asteroid belt and among the Trojan asteroids that share Jupiter's orbit. D-type asteroids are rich in organic compounds, possibly including complex carbon molecules. If Oumuamua is essentially a D-type asteroid that originated in another solar system, its composition might tell us something about how those compounds form. D-type asteroids in our own system are thought to have formed in the outer solar system, beyond the snow line where water ice could condense. Their reddish color and low albedo suggest organic-rich surfaces. If Oumuamua matches this category, it might have formed in the outer regions of its parent system before being ejected during gravitational interactions with giant planets. But the simple categorization as a D-type asteroid doesn't solve the mystery. D-type asteroids don't have anomalous accelerations. They don't have extreme shapes. They follow normal rotational dynamics. Oumuamua's behavior was strange enough that calling it a generic D-type asteroid felt inadequate, even if its colors matched. Throughout the observation campaign, the object was getting fainter every night. At its peak brightness, shortly after discovery, Oumuamua was about 19th magnitude, faint but detectable with medium-sized telescopes. Within a few weeks, it had dimmed to 22nd magnitude, requiring the largest telescopes. By mid-November, it was below 24th magnitude. Only Hubble and a few of the largest ground-based telescopes could still see it. By December, only the most sensitive instruments could detect it at all. The fading was caused by Oumuamua's growing distance from both the Sun and Earth. Less sunlight reached the object, so it reflected less light. The light that did reflect had to travel farther to reach us, spreading out over a larger area in space. Both effects combined to make the object dim rapidly by approximately the fourth power of its distance from the Sun. Doubling the distance meant becoming 16 times fainter. Astronomers worked against this fading curve with everything they had. They used adaptive optics to remove atmospheric blurring. They stacked multiple exposures to extract the faintest signals. They observed at every available wavelength to maximize the data collected. The total amount of light gathered from Oumuamua over the entire observation campaign was extraordinarily small. From the largest ground-based telescopes, individual exposures collected only a few hundred photons from the object. The entire scientific understanding of this interstellar visitor came from analyzing those photons. In January 2018, the Hubble Space Telescope made its final observations of Oumuamua. By this point, the object was about 2.9 astronomical units from Earth, roughly the distance of the asteroid belt. It had faded to about magnitude 27, which is fainter than almost anything Hubble had ever attempted to observe. The observation succeeded only barely, with the signal so weak that careful processing was needed to distinguish Oumuamua from background noise. These final observations are what allowed Marco Micheli's team to measure the anomalous acceleration with confidence. By tracking the object's position over the longest possible baseline, they could detect the small deviation from a purely gravitational trajectory. After January 2018, Oumuamua was effectively gone. A few attempts were made with the largest ground-based telescopes to observe it later, but the object had dimmed below the detection threshold of any available instrument. It continued to recede, growing more distant every day, but humanity could no longer see it. Calculations show where Oumuamua is now and where it will be in the future. It's heading roughly toward the constellation Pegasus. By 2026, nearly 9 years after discovery, the object is about 30 astronomical units from the Sun, approximately the distance of Neptune's orbit. It's invisible to all our telescopes. It's traveling at about 26 kilometers per second relative to the Sun, having been gravitationally decelerated by solar gravity, but still moving fast enough to never return. The trajectory will carry Oumuamua outward indefinitely. In about 10,000 years, it will be approximately 700 astronomical units from the Sun, well beyond the heliopause that the Voyager spacecraft crossed. By that point, it will once again be in pure interstellar space, having completed its brief visit to our solar system. It will continue traveling for millions of years, perhaps eventually passing through other planetary systems, perhaps never encountering another star. The total time humanity had to study an object from another star system was approximately 11 weeks of useful observations, from late October 2017 through early January 2018. In that brief window, we gathered enough data to know that Oumuamua was profoundly strange, but not enough to understand exactly what it was. The mystery has only deepened as scientists have continued to analyze the data in the years since. What we needed was another interstellar object, one that we could discover earlier and study longer. We didn't have to wait long for another interstellar visitor, though the second one turned out to be very different from Oumuamua, and in ways that made the mystery of the first even deeper. On August 30, 2019, an amateur astronomer named Gennady Borisov, working from his own private observatory in Crimea, detected a comet-like object on his telescope. Borisov had built his own telescope, ground his own mirrors, and operated his observatory as a hobby. He had discovered several comets before, but this one looked different. Its motion seemed too fast for a normal solar system comet. He reported his observation to the Minor Planet Center, and within days, professional astronomers had confirmed his suspicion. The object had a clearly hyperbolic orbit. It was the second interstellar object ever detected. The new visitor was officially named 2I/Borisov, with the 2I indicating it was the second interstellar object discovered. Unlike Oumuamua, which had been discovered on its outbound trajectory after its closest approach to the Sun, Borisov was detected before perihelion. Astronomers would have months to observe it as it approached the Sun, made its closest approach, and headed back out. This was the opportunity they had been hopping for ever since Oumuamua disappeared. The first detailed observations confirmed that Borisov was nothing like Oumuamua. It was clearly a comet. It had a visible coma, a tail, and obvious outgassing. Spectroscopic observations detected cyanide, carbon monoxide, water, and the other typical cometary compounds. The object was perhaps 200 to 500 meters in diameter, similar in size to Oumuamua, but its behavior was completely conventional. If you didn't know its trajectory, you might have mistaken Borisov for an ordinary comet from our own Oort cloud. This was both fascinating and frustrating. Fascinating because it confirmed that the prediction had been correct. Interstellar objects should mostly be comets, ejected from the icy outer regions of their parent planetary systems. Borisov fit this expectation perfectly. Frustrating because it made Oumuamua's anomalies even more puzzling. If Borisov was the typical interstellar visitor, what was Oumuamua? Detailed studies of Borisov over the following months added to the puzzle. The Hubble Space Telescope obtained some of the highest resolution images ever taken of an interstellar object, showing the comet's structure in detail. The European Southern Observatory measured its composition with extraordinary precision. The carbon monoxide content was much higher than typical for comets in our solar system. The ratio of carbon monoxide to water was nearly 3 times higher than in any comet previously studied. This suggested Borisov had formed in a particularly cold region of its parent system, where carbon monoxide could remain frozen in significant quantities. The composition was telling us something about the parent star system. Cold conditions during planet formation favor the accumulation of carbon monoxide and other volatile ices. Borisov apparently formed in such a cold environment, far from its parent star. This is consistent with the standard picture of how planetary systems work. Comets and icy bodies form in the outer regions where temperatures are low enough for volatiles to condense. Gravitational interactions with giant planets then eject some of these bodies into interstellar space. Borisov, then, gave us a glimpse of the typical interstellar object. A comet, perhaps slightly different from comets in our own system, but recognizably part of the same family of icy bodies that populate the outer regions of planetary systems. Its journey to our solar system was a normal story of formation in a cold outer region, ejection through gravitational interaction with a giant planet, and millions of years drifting through interstellar space before encountering our star. If Borisov is normal, then Oumuamua is profoundly abnormal. The contrast between the two objects highlights how strange Oumuamua really was. Borisov showed all the expected behaviors. Oumuamua showed almost none of them. Borisov had a visible coma and tail. Oumuamua had nothing. Borisov had a normal cometary composition. Oumuamua had whatever composition was producing invisible acceleration. Borisov had a reasonably normal rotation. Oumuamua was tumbling chaotically. Borisov was roughly spherical based on its imaging. Oumuamua was extremely elongated. Two interstellar objects, both passing through our solar system within 2 years of each other. One conforms to all our expectations. The other defies them at almost every level. The contrast makes Oumuamua's strangeness more striking, not less. If interstellar objects were simply diverse and unpredictable, we might expect a wider range of behaviors. But Borisov fits the prediction so well that Oumuamua's deviations seem all the more remarkable. Borisov continued through our solar system on a conventional cometary path. It reached perihelion on December 8, 2019, passing about 2 astronomical units from the Sun, somewhat beyond Mars's orbit. As it warmed, it became more active, with its coma growing brighter and its tail extending. In early March 2020, just as the world was beginning to focus on the emerging COVID-19 pandemic, Borisov underwent a dramatic outburst. Its brightness increased significantly, and Hubble images suggested the nucleus might have actually fragmented, breaking into 2 pieces. This kind of fragmentation is occasionally observed in our own cometary population when a comet passes too close to the Sun and is broken apart by tidal stress and outgassing pressure. Borisov apparently couldn't survive the encounter with our star intact. The fragmentation provided unique scientific opportunities. By observing the separate pieces and how they evolved, astronomers could learn about the comet's internal structure. The fragments behaved like normal cometary debris, gradually dispersing and fading. By late 2020, Borisov was on its outbound trajectory, faded significantly, and heading back toward interstellar space. Like Oumuamua, it would never return. But while Borisov was visible and being studied, scientists kept analyzing the data they had on Oumuamua. New papers continued to appear. Some refined the size estimates. Others reinterpreted the brightness variations to suggest different shapes. Some focused on the acceleration, trying to explain it through various unconventional mechanisms. The debate over what Oumuamua actually was continued and intensified. One important development came in 2023 when a team led by Jennifer Borgner and Daryl Seligman published a paper proposing a new natural explanation for Oumuamua's behavior. Their hypothesis focused on the possibility that Oumuamua's surface contained molecular hydrogen, but not as pure hydrogen ice. Instead, the hydrogen would be trapped within a matrix of water ice. The proposal was that cosmic ray bombardment over millions of years could process water ice to produce hydrogen, which would then be trapped in the ice's structure. When Oumuamua approached the Sun, solar heating would release this trapped hydrogen, producing acceleration without the visible spectroscopic signatures of normal cometary outgassing. The Borgner-Seligman hypothesis has more physical plausibility than the pure hydrogen iceberg idea. Molecular hydrogen trapped within water ice is a known phenomenon. Laboratory experiments have shown that radiation processing of water ice can produce significant amounts of trapped hydrogen. The hypothesis explains why no normal water emission was detected. Most of the water would remain frozen, with only the trapped hydrogen being released. The acceleration could then come from this hydrogen outgassing, which would be largely invisible at the wavelengths astronomers were observing. This hypothesis represents the most carefully developed natural explanation for Oumuamua's behavior. It has gained some traction in the astronomical community, but it has not become universally accepted. Critics have noted several problems. The amount of hydrogen needed to produce the observed acceleration is substantial, requiring efficient trapping during the formation process. The hypothesis also requires that Oumuamua somehow survived in interstellar space long enough to be processed by cosmic rays, but didn't undergo significant erosion. The detailed parameters need to be just right for the model to work. Even more importantly, the Borgner-Seligman hypothesis doesn't address all of Oumuamua's anomalies. The extreme shape remains unexplained. Why was the object so elongated? Why did it tumble chaotically? These features of the object are not directly addressed by the hydrogen outgassing hypothesis, even if that hypothesis explains the acceleration successfully. Avi Loeb has continued to argue that the artificial hypothesis remains viable. In multiple papers and his book, he has developed the idea that Oumuamua might be a defunct piece of alien technology. He points out that each natural explanation requires specific and somewhat unusual circumstances. A hydrogen iceberg requires implausibly cold formation conditions. A nitrogen fragment requires a specific kind of impact event on a Pluto-like body. The hydrogen trapped in water hypothesis requires precise parameters that fall within a narrow range. At what point, Loeb asks, do these natural explanations become more contrived than the artificial alternative? The debate has expanded beyond the specific case of Oumuamua to encompass broader questions about how science should handle anomalous observations. Loeb has been vocal in arguing that scientific conservatism, the tendency to prefer natural explanations even when they require unusual circumstances, can become a barrier to discovery. If alien artifacts are passing through our solar system, refusing to consider that possibility would mean missing the most important discovery in human history. Other scientists argue that scientific conservatism is exactly what protects us from making unsupported extraordinary claims. Both sides have legitimate points. What's clear is that the data we have on Oumuamua is unlikely to settle the debate. The observations we have are simply not sufficient to definitively determine the nature of the object. Without higher resolution images, without spectroscopic identification of specific compounds, without direct measurements of its composition, we cannot rule out either the natural or artificial hypotheses. The debate must continue based on the limited data we possess. This is part of why future interstellar object detections are so important. Each new discovery offers a chance to test our hypotheses. Borisov gave us our first chance, and it showed us what a normal interstellar object looks like. The third interstellar object, when it is discovered, may give us another point of comparison. Eventually, we will accumulate enough examples to understand the typical population of interstellar objects, and then we can determine where Oumuamua fits in that distribution. The challenge is that interstellar objects are rare. Despite the calculations suggesting they should pass through the inner solar system fairly often, only two have been confirmed since modern surveys began. This is partly because they're hard to detect. Most are probably too small to see, or they pass too far from Earth to be noticed. The two we have detected are likely among the largest and brightest examples, the ones that happen to come closest. The actual population of interstellar objects passing through our solar system is much larger than what we've observed. Several new survey telescopes are coming online or being planned that should dramatically increase our detection rate. The Vera Rubin Observatory in Chile, which began regular operations in 2025, has an 8.4-meter telescope dedicated to surveying the sky. It can image enormous areas of sky with great sensitivity. Astronomers expect Rubin to detect many new interstellar objects per year, possibly dozens. The Vera Rubin Observatory represents a transformative leap in our ability to detect interstellar objects, and understanding why requires appreciating just how much the field of astronomy has changed in the years since Oumuamua's discovery. When PAN-SDARS spotted Oumuamua in October 2017, it was operating at the leading edge of what survey telescopes could do. 8 years later, the technology has advanced dramatically. Rubin's primary mirror is more than 4 times the area of PAN-SDARS's. Its detector covers a wider field of view. Its sensitivity is greater. Its observing cadence is faster. Every 2 days, Rubin scans the entire visible sky. Every object that moves against the background stars is automatically detected, catalogued, and analyzed by sophisticated software. For interstellar objects, this means several things. First, Rubin should detect them earlier, often before they reach perihelion. This was the major limitation with Oumuamua. By the time astronomers found it, the closest approach to the Sun had already happened. Any cometary activity that might have occurred during the warming phase had passed. With Rubin detecting objects on their inbound trajectories, we could watch interstellar visitors approach the Sun, observe what happens as they warm, and study them throughout their entire passage. Second, Rubin should detect smaller objects than previous surveys. The current detection threshold for interstellar objects is probably around 100 meters. Rubin can potentially see objects half that size. The population of small interstellar objects must be much larger than the population of large ones, just as smaller asteroids vastly outnumber larger ones in our own solar system. We may find dozens of interstellar objects per year, perhaps eventually hundreds. And then there is the third interstellar object, which has its own story to tell. In July 2025, astronomers using the Atlas survey detected another object on a clearly hyperbolic trajectory. The discovery was made by a network of telescopes designed primarily to detect potentially hazardous asteroids approaching Earth. The new object was officially designated 3I Atlas, following the convention established with Oumuamua and Borisov. 3I Atlas turned out to be intermediate between its two predecessors in some ways. It showed clear cometary activity, with a visible coma and tail, similar to Borisov. Its composition was studied with multiple telescopes, including the James Webb Space Telescope, which had not been operational during Oumuamua's brief visit. The Webb observations revealed details about cometary chemistry that had been impossible to obtain for the earlier interstellar objects. The composition appeared broadly similar to Borisov's, with relatively high concentrations of carbon dioxide and other volatile ices, again suggesting formation in a cold outer region of its parent system. But 3I Atlas showed its own peculiarities. Its trajectory passed somewhat closer to the inner planets than either of the previous interstellar objects. Its rotation properties were different from both Oumuamua and Borisov. Some early analyses suggested it might have an elongated shape, though not as extreme as Oumuamua's. The object was bigger than the previous two interstellar visitors, perhaps a kilometer or more in diameter, which made it easier to study despite being further from Earth. Astronomers had months to observe it as it approached and passed the Sun. The discovery of 3I Atlas gave the scientific community its first chance to apply lessons learned from Oumuamua and Borisov. Observation strategies that had been developed in hindsight could now be applied prospectively. Coordinated campaigns involving telescopes around the world were organized far in advance. Spectroscopic observations were planned at multiple wavelengths and at different points along the trajectory. The result was the most comprehensive study of an interstellar object ever conducted. Even with all these observations, however, 3I Atlas did not definitively resolve the mystery of Oumuamua. The newer object's behavior was unusual in its own ways, but generally fell within the range expected for cometary bodies. It didn't show Oumuamua's extreme combination of anomalous acceleration without visible outgassing. Its shape, while perhaps somewhat elongated, was not nearly as extreme. It was, in many ways, a more conventional cometary visitor with its own minor peculiarities. This pattern, with two relatively normal cometary visitors flanking the strange case of Oumuamua, makes Oumuamua's anomalies stand out even more starkly. If we had only ever observed Oumuamua, we might wonder whether interstellar objects were generally strange in ways we didn't understand. With Borisov and 3I Atlas as comparison cases, both showing relatively conventional behavior, Oumuamua appears even more unusual within the small sample of interstellar objects we've observed. Some astronomers have begun to wonder whether Oumuamua might represent a rare class of object that simply hasn't been encountered again. There are many possible categories of interstellar bodies, and we've sampled only 3 so far. Maybe Oumuamua belongs to a population that's relatively uncommon. The other categories might include fragments of disrupted planets, exotic ices from unusual formation environments, or bodies that have undergone unusual processing during their interstellar journey. Without more examples, we simply cannot determine which possibilities are most likely. The hope is that future detections will eventually clarify the picture. If the Vera Rubin Observatory begins detecting interstellar objects at the predicted rates, we should accumulate dozens of examples within a few years. Among that larger sample, we should find more objects with unusual properties. If Oumuamua-like objects are out there, we should eventually find more of them. If they're truly rare, then Oumuamua becomes either an extreme statistical outlier or something genuinely exceptional. In the meantime, the analysis of Oumuamua's data continues. New techniques are being applied to extract additional information from the limited observations. Researchers have developed sophisticated photometric models that try to constrain the object's shape and reflectivity. Statistical analyses examine whether the observed properties are consistent with various natural origin scenarios. Theoretical work continues on the formation of unusual interstellar objects, exploring what kinds of environments might produce bodies with Oumuamua-like characteristics. One particularly interesting line of research concerns the population of objects that could be ejected from disrupted planetary systems. When a star reaches the end of its life and becomes a red giant or white dwarf, the resulting changes can destabilize any planetary system around it. Material that was previously in stable orbits can be flung out at high speed. Calculations suggest that the death throes of stars should produce substantial populations of small objects ejected into interstellar space. Some of these objects might have unusual compositions reflecting the late stages of stellar evolution. If Oumuamua came from such a disrupted system, its strange properties might reflect that violent origin. Material processed by a dying star, exposed to intense radiation during the disruption, then ejected with a tumbling motion from the chaos, could potentially explain some of the observed features. The hypothesis is speculative, but it represents the kind of natural explanation that researchers are continuing to develop. Each new theoretical framework adds another possible solution to the mystery, even if none has yet gained universal acceptance. The question of why interstellar object detections are increasing also deserves attention. Pan-SDARS had been operating for 7 years before it detected Oumuamua. Borisov was found 2 years later. 3I Atlas was found 6 years after that. The detection rate is increasing because the technology is improving, but also because we're better at recognizing interstellar objects when we see them. The protocols for identifying potential interstellar candidates have been refined. The software that scans survey data has been updated to flag unusual trajectories. Astronomers are primed to look for hyperbolic orbits in their data. This raises an interesting historical question. Could earlier interstellar objects have passed through our solar system undetected? The answer is almost certainly yes. Before sensitive survey telescopes existed, anything smaller than about a kilometer would have been very difficult to see. Even larger objects might have passed close to the Sun without being noticed, particularly if they happened to be on the far side of the Sun during their closest approach. The interstellar visitors before 2017 went undetected not because they weren't there, but because we lacked the tools to find them. This historical reality has implications for how we should think about the population of interstellar objects. The bodies we've detected are likely just the tip of an iceberg. Many more must be passing through the solar system, some quite close to Earth, that we simply haven't seen yet. The improving survey capabilities should reveal more of them in coming years. The improving capabilities also raise the possibility of sending spacecraft to intercept future interstellar objects. This idea has been proposed multiple times since Oumuamua's brief visit. The European Space Agency has approved a mission concept called Comet Interceptor, which would launch a spacecraft to a parking orbit between Earth and the Sun. The spacecraft would wait until an interesting target was detected, then use its onboard propulsion to maneuver into an intercept trajectory. The primary target would be a long-period comet from the Oort cloud, but the mission could potentially be redirected to an interstellar object if a suitable one was detected at the right time. Comet Interceptor is scheduled to launch around 2029. By that point, the Vera Rubin Observatory should be operating at full capacity, dramatically increasing the rate of interstellar object detections. The combination of a waiting spacecraft and rapid survey detection could enable the first close-up study of an interstellar object. Even a brief flyby would yield observations far beyond what ground-based telescopes can achieve. Direct imaging could resolve the object's shape. Mass spectrometry could identify its composition. Magnetometry could detect any magnetic field. The amount of new information would be transformative, but even Comet Interceptor would have limitations. The spacecraft would only have a brief encounter as it flew past its target, perhaps a few minutes of close observation. The amount of data collected would be enormous compared to remote observations, but it would still be a brief glimpse. For more detailed study, we would need a mission that could rendezvous with an interstellar object and travel alongside it, observing over an extended period. Such a mission would require significantly faster spacecraft than anything we've built. The interstellar objects are moving so fast through our solar system that catching up to them is difficult with current propulsion technology. Various concepts for higher speed missions have been proposed. Nuclear thermal propulsion could provide higher exhaust velocities than chemical rockets, potentially enabling more demanding interception missions. Solar electric propulsion, using sunlight to power ion engines, could provide sustained acceleration over long periods. Solar sails could harness the pressure of sunlight for propulsion, particularly effective for missions that begin close to the sun. Each of these technologies has been demonstrated in some form, but none has yet been used for a mission requiring the kind of high velocities needed to rendezvous with interstellar objects. The longer-term hope is that improving propulsion technology will eventually enable detailed study of interstellar visitors. If we develop the ability to send spacecraft to rendezvous with these objects rather than just fly past them, we could finally answer many of the questions that Oumuamua left unresolved. We could determine the composition with certainty. We could observe the shape directly. We could measure the acceleration mechanism in detail. We could perhaps even return samples to Earth for laboratory analysis. Until then, we are limited to remote observations. We can study the photons that reach us from these distant visitors. We can analyze their trajectories. We can speculate about their origins. The Avi-Loeb hypothesis deserves a careful examination on its own terms, separate from the question of whether it is ultimately correct. Loeb is not a fringe figure proposing wild ideas. He is one of the most accomplished astrophysicists working today. He served as chair of Harvard's astronomy department for 9 years, longer than any predecessor in that role. He has published hundreds of peer-reviewed papers across many subfields of astronomy. He has been involved in major projects including the Breakthrough Initiatives, which fund searches for extraterrestrial intelligence. When someone with this background suggests that an unusual object passing through our solar system might be artificial, the suggestion deserves serious engagement, even from those who disagree with it. Loeb's argument proceeds through several steps. First, he documents the anomalies of Oumuamua, the extreme shape, the anomalous acceleration, the lack of visible outgassing, the reddish color, the chaotic tumbling, the trajectory that came suspiciously close to the local standard of rest. Each of these features individually might be explainable through natural processes, though sometimes only through unusual or contrived scenarios. Combined, they form a pattern that strains every natural hypothesis. Second, Loeb argues that the natural hypotheses have specific problems. The hydrogen iceberg hypothesis, in its original pure form, is physically problematic because hydrogen ice may not survive long interstellar journeys. The nitrogen fragment hypothesis requires specific origin scenarios that are statistically unlikely. The hydrogen trapped in water hypothesis from Bergner and Seligman, while more plausible, has its own parameter constraints and doesn't explain all the observations. Each natural hypothesis explains some anomalies but leaves others unexplained or requires specific circumstances that seem unlikely. Third, Loeb proposes that an artificial origin would explain the observations naturally. A thin, flat object designed for light sail propulsion would naturally show extreme brightness variations as it rotated. It would naturally experience acceleration from solar radiation pressure without producing visible outgassing. Its shape, while unusual for natural objects, would be entirely sensible for engineered technology. The lack of visible activity becomes a feature rather than a bug. The object is doing exactly what such a technology should do. Fourth, Loeb argues that the prior probability of artificial objects passing through our solar system is not zero. We don't know how common technological civilizations are in the galaxy. The Drake equation, which attempts to estimate the number of communicative civilizations in our galaxy, has factors with enormous uncertainties. Some plausible estimates suggest there should be millions of technological civilizations. Other estimates suggest there might be none other than us. Without better data on this question, we cannot rule out the existence of alien technology drifting through space. Fifth, Loeb argues for a particular epistemological stance. When we encounter genuinely anomalous observations, we should consider all hypotheses that could explain them, including unconventional ones. Refusing to consider artificial origins for objects with strange properties means we will never recognize alien artifacts, even if they pass through our solar system. The choice not to investigate is itself a choice with consequences. The reaction from the scientific community has been complicated. Most working astronomers do not accept the artificial hypothesis as the most likely explanation. They argue that natural explanations, even ones requiring unusual circumstances, should be preferred over invoking unknown alien civilizations. The principle of parsimony, properly applied, favors known phenomena over speculative ones. Even if natural explanations require some specific circumstances, those circumstances might still be more likely than the existence of detectable alien technology in our solar system. Some critics have gone further, accusing Loeb of damaging public understanding of science by promoting what they consider speculation as legitimate possibility. They argue that talking about alien artifacts attracts media attention, but distorts the actual state of evidence. Loeb has been called everything from a serious heterodox thinker to a publicity seeker. The personal dimensions of the debate have sometimes overshadowed the scientific issues. In response, Loeb has consistently maintained that his arguments are based on the evidence and on standard scientific reasoning. He points out that proposing hypotheses is part of scientific work, and that any hypothesis consistent with the evidence deserves consideration. The fact that a hypothesis is uncomfortable or unconventional doesn't make it wrong. Science has many examples of unconventional hypotheses that turned out to be correct. Continental drift was once dismissed as fringe. Bacterial causes of ulcers were ridiculed before becoming accepted. Even the existence of meteorites was denied for centuries because scientists couldn't believe that rocks could fall from the sky. The Galileo Project, which Loeb founded in 2021, represents an attempt to put the search for unusual objects on a more systematic footing. The project aims to develop dedicated instruments to detect and study unusual aerial phenomena and unusual interstellar objects. If alien technology is occasionally passing through our environment, the project seeks to be ready to detect it the next time. The project has attracted significant funding and involves multiple researchers. Its scientific output so far has been modest, but it represents an effort to take the question seriously. Whether or not Oumuamua was artificial, the debate it has generated has been valuable. The question of how science should handle anomalous observations is a real and important one. The willingness to consider unconventional hypotheses is part of what allows science to make discoveries. The constraints against accepting unconventional hypotheses too readily is what prevents science from being overrun by unsupported speculation. Finding the right balance between these tendencies is an ongoing challenge. The debate has also focused attention on the search for extraterrestrial intelligence more broadly. For decades, this search has been conducted primarily through radio astronomy, with telescopes listening for signals that might indicate technological civilizations. The implicit assumption has been that aliens, if they exist, would communicate using radio waves similar to our own. The discovery of Oumuamua and the subsequent debate has prompted some researchers to consider other possibilities. Aliens might not communicate at all. They might send physical probes rather than radio signals. They might have left technology behind that we could find with the right instruments. The search for alien intelligence might need to expand beyond traditional radio searches. This expansion has practical consequences. New instruments are being designed to look for unusual phenomena that might indicate technology. Lasers, which would be the natural choice for communication over long distances, are being searched for in addition to radio. Spectroscopic signatures of artificial atmospheres on distant planets are being sought. Even the possibility of finding artifacts in our own solar system has gained renewed attention. The Vera Rubin Observatory will detect any unusual objects in the inner solar system. If interstellar artifacts exist, we have a better chance than ever before of finding them. The mystery of Oumuamua, then, has implications well beyond the specific question of what that one object was. It has raised broader questions about how we should search for life and intelligence in the universe. It has challenged scientific conventions about what hypotheses deserve consideration. It has prompted new technological developments aimed at better detection of unusual phenomena. Returning to Oumuamua specifically, we should examine the strongest natural hypotheses in more detail. The Bogner-Seligman hypothesis about hydrogen trapped in water ice represents one of the most carefully developed natural explanations. Let's understand exactly what it proposes and why it might or might not work. The basic idea begins with the recognition that water ice in interstellar space is exposed to cosmic rays for very long times. Cosmic rays are extremely energetic particles, primarily protons, that travel through the galaxy at relativistic speeds. When they strike water ice, they can break apart the water molecules and produce hydrogen gas. Some of this hydrogen escapes immediately. Some becomes trapped within the ice structure, occupying small voids or sites where hydrogen molecules can fit without disrupting the surrounding water. Laboratory experiments have demonstrated this process. When water ice samples are irradiated under conditions similar to interstellar space, hydrogen is produced, and some of it does indeed become trapped. The trapped hydrogen can later be released when the ice is warmed, returning to gaseous form. The release happens at temperatures well below the sublimation point of water, meaning hydrogen can escape while the water itself remains frozen. For Oumuamua, the hypothesis proposes that the object accumulated significant hydrogen during its interstellar journey through this process. When it approached the Sun, solar heating released the trapped hydrogen, producing acceleration. Because hydrogen is invisible at the wavelengths astronomers were observing, the outgassing wasn't detected. The water itself remained solid, so no water vapor was produced. The acceleration could be explained without violating the observational constraints. The hypothesis requires several conditions to work. First, Oumuamua needs to contain a significant amount of water ice. This is plausible for an object from outer regions of a planetary system. Second, it needs to have spent enough time in interstellar space to accumulate hydrogen through radiation processing. Estimates suggest this requires perhaps hundreds of millions of years. Third, the hydrogen needs to be released efficiently when warmed. Fourth, the amount of hydrogen released needs to be substantial enough to produce the observed acceleration, but not so much that it would have noticeable spectroscopic signatures. The hypothesis has plausibility in its favor, but it also has problems. The amount of hydrogen needed is substantial. Calculations suggest that hydrogen would need to be trapped at concentrations near the maximum possible levels for the proposed mechanism to work. The hypothesis also doesn't explain why Oumuamua had such an extreme shape. Cosmic ray processing of water ice doesn't naturally produce highly elongated bodies. The shape would need to be explained through some separate mechanism, perhaps the original formation process or a violent ejection event. Critics have noted that the Bogner-Seligman hypothesis is essentially a sophisticated way of saying that Oumuamua might be a comet with unusual composition. The basic narrative is still cometary, just with a specific composition that explains why the cometary signatures weren't observed. This pushes the explanation toward something we can call natural while requiring specific and somewhat unusual circumstances. The strongest argument for natural explanations, in general, is that we have only observed one example of a strange interstellar object. Among the three interstellar objects detected so far, only Oumuamua showed the dramatic anomalies. The other two were relatively conventional. If Oumuamua-like objects are rare, then finding one might still be consistent with natural processes that produce unusual objects occasionally. Statistical reasoning suggests we should be cautious about drawing strong conclusions from a single example. The next Oumuamua-like object, when and if it appears, will tell us much more about whether such bodies are common natural phenomena or genuinely exceptional. In the meantime, the debate continues without resolution. Oumuamua remains a mystery, and the answer to what it actually was remains beyond our current capability to determine with certainty. The historical context of Oumuamua's discovery deserves more attention because it reveals how dramatically our understanding of the solar system has changed in just the past few decades. For most of human history, the solar system was thought to consist of the sun, the planets, and their moons. The space between planets was considered essentially empty. Comets were viewed as mysterious occasional visitors whose origins were debated. Asteroids weren't even known until 1801, when Ceres was discovered, and for decades after that they were considered exotic curiosities rather than evidence of a major population of bodies. The recognition that the solar system contains enormous populations of small bodies came gradually through the 20th century. Astronomers identified the asteroid belt between Mars and Jupiter. They mapped the orbits of comets and proposed that most originated in a distant reservoir. Jan Oort, the Dutch astronomer, proposed in 1950 that comets came from a vast spherical cloud surrounding the solar system at distances of tens of thousands of astronomical units. This Oort cloud, as it became known, would contain trillions of icy bodies, each potentially capable of being perturbed into the inner solar system to become a visible comet. The Kuiper belt was proposed even earlier, in the 1940s, by Kenneth Edgeworth and Gerard Kuiper as a closer reservoir of icy bodies just beyond Neptune's orbit. The first confirmed Kuiper belt object, other than Pluto itself, wasn't discovered until 1992. Since then, over 3,000 such objects have been catalogued. Kuiper belt has turned out to be far more populous and complex than initially imagined. It contains multiple distinct populations of objects, including the classical Kuiper belt, scattered disk objects, resonant populations locked into orbits related to Neptune's, and the more distant detached objects that extend beyond the gravitational influence of the major planets. By the early 21st century, astronomers understood that our solar system was filled with small bodies. Hundreds of millions of asteroids in the main belt, trillions of comets in the Oort cloud, tens of thousands of large bodies in the Kuiper belt, and untold smaller ones. The solar system was not the simple system of planets and empty space that had been imagined just a century earlier. It was a complex, populated system with material at every distance from the sun. This recognition raised an obvious question. If our solar system contains so much small body material, what about other solar systems? If we eject material into interstellar space, do they too? The answer had to be yes. The same gravitational processes that operate in our system should operate elsewhere. Other planetary systems should produce ejected objects at comparable rates. Over the age of the galaxy, the cumulative ejection should have produced enormous populations of interstellar objects drifting between the stars. Calculations of these populations were attempted starting in the 1970s. The estimates varied widely depending on the assumed ejection efficiencies and the assumed densities of small bodies in other systems. But all the estimates agreed that interstellar objects should be common. They should pass through any given star system regularly. The reason none had been detected, despite their predicted abundance, was simply the difficulty of seeing them. Most would be small. They would move quickly across the sky. They would be visible only briefly during their passage through the inner solar system, where they could be illuminated by the local star. The detection of Oumuamua, then, was a confirmation of long-standing predictions. The basic idea had been right. Interstellar objects do exist, and they do pass through our solar system. The surprise was not that an interstellar object was finally detected, but that the specific object that was found turned out to be so strange. The astronomers had been expecting an interstellar object. They had not been expecting one with Oumuamua's particular properties. This historical perspective is important because it changes how we should interpret Oumuamua's anomalies. If interstellar objects had never been predicted, then the discovery of any such object would have been profound. The strange properties of Oumuamua might have been viewed as the natural features of a previously unknown class of body. But because the existence of interstellar objects was predicted and the typical properties were expected to be cometary, Oumuamua's strangeness stood out against expectations. The deviation from prediction is what makes the object so interesting. The history of the field also explains why Borisov was received so calmly compared to Oumuamua. Borisov fit expectations. It was a comet. It came from interstellar space, but it did so by being recognizable as a cometary body. Astronomers were not surprised by Borisov because they had been expecting exactly that kind of object. The discovery was scientifically important, providing the first confirmation of the cometary interstellar object population. But it wasn't shocking. Oumuamua had been the shock. Now we should examine the question of what the interstellar medium itself does to objects passing through it for millions of years. This is relevant because Oumuamua, regardless of its origin, definitely spent a long time in interstellar space before encountering our solar system. The properties we observed when it visited us were not the properties it had when it left its parent system. Whatever it was, it had been altered by its journey. The interstellar medium is mostly empty by terrestrial standards. The average density is about 1 atom per cubic centimeter, which is far thinner than the best vacuums we can produce in laboratories. But across the enormous distances and times involved in interstellar journeys, even this thin medium has effects. Cosmic rays continuously bombard any object drifting through it. Dust grains occasionally impact the surface. The constant exposure to the harsh radiation environment slowly modifies surface chemistry and physical properties. For a body the size of Oumuamua, traveling for perhaps hundreds of millions of years through the galaxy, the cumulative effects of interstellar processing must be substantial. The surface composition will be altered by radiation chemistry. Volatile materials might gradually escape into space. The physical structure could be modified by repeated thermal cycling as the object passed through warmer and colder regions of the galaxy. The original object that began its journey from another star system would not be the same as the object that arrived at our sun. It would have been weathered by the long passage. This complicates any attempt to determine Oumuamua's origin. Even if we could identify some surface property that matched a known type of natural object, we couldn't be certain whether that property had been present from the beginning or whether it had developed during interstellar transit. The reddish color, for instance, could be original or could be the result of cosmic ray processing during the journey. The lack of detectable ices could mean Oumuamua never had any, or it could mean any ices it had once contained had been removed during its long travel. The processing during transit also raises the question of whether Oumuamua could have changed shape during its journey. A loosely held body might have lost material gradually, becoming more elongated over time. Erosion by cosmic rays and occasional dust impacts could have preferentially removed material from certain regions of the surface. By the time we observed Oumuamua, its shape might have been very different from its original shape. The extreme elongation might be a consequence of the journey rather than a feature of the original body. This line of thinking leads to some unusual possibilities. If interstellar objects can be shaped by their journey through the galactic medium, then objects that have traveled longer would tend to be more processed. Among the population of interstellar objects, we might expect to find a range of weathering states. Some would be relatively pristine, having only recently been ejected from their parent systems. Others would be heavily processed, having traveled for billions of years before encountering another star. The dynamical age of an interstellar object can sometimes be estimated from its velocity relative to the local standard of rest. As mentioned earlier, the longer an object has been drifting, the more its velocity tends to converge toward the average motion of nearby stars. Oumuamua's velocity was unusually close to the local standard of rest, suggesting a possibly long dynamical age. If Oumuamua had been traveling for billions of years, the cumulative effects of interstellar processing would have been substantial. But there's a counter-argument. If Oumuamua had been drifting for billions of years, it should have lost most of its volatile materials long ago. The Hydra, in water ice hypothesis, requires that significant amounts of trapped hydrogen still be present after the long journey. The very long journey scenarios are difficult to reconcile with the proposed natural explanations for the observed acceleration. We end up with a tension. The dynamics suggest long timescales. The chemistry suggests shorter timescales. Resolving this tension requires careful modeling. Some researchers have proposed compromise scenarios. Oumuamua might have been processed by cosmic rays for a moderately long time, perhaps a few 100 million years. This would be enough to redden its surface and produce some chemical changes without removing all volatile compounds. The object's velocity might be close to the local standard of rest because it originated from a particular type of stellar population, not because it has been drifting for billions of years. These intermediate scenarios are plausible but difficult to test without additional observations. The varied state of preservation of interstellar objects also has implications for what we should expect to find as we continue to discover them. The first few examples might be biased toward objects that are easier to detect, perhaps because they're brighter or because they happen to come close to Earth. As detection capabilities improve and the sample size grows, we should encounter a wider range of objects with different histories and properties. Some will be cometary like Borisov. Others might be more like Oumuamua. Still others might show properties we haven't yet seen. The James Webb Space Telescope has begun playing a significant role in studying interstellar objects. Webb's infrared capabilities allow it to detect spectral signatures that ground-based telescopes cannot easily measure. The observations of 3I Atlas revealed compositional details that would have been impossible to obtain for Oumuamua. As more interstellar objects are detected, Webb and its successors will be able to characterize them in unprecedented detail. The accumulating database will allow statistical comparisons between objects and the development of better understanding of the interstellar object population. In the longer term, the Habitable Worlds Observatory, currently being designed as a successor to Webb, should provide even better capabilities for studying small bodies. The Atacama Large Millimeter Array continues to be a powerful tool for cometary studies. Future radio telescopes will further enhance our ability to detect specific molecules and characterize compositions. Each new facility adds to our toolkit for understanding what interstellar visitors bring with them when they pass through our solar system. The combined effort represents one of the most active areas of contemporary astronomy. What began with a single anomalous detection in October 2017 has expanded into a substantial subfield of research. The implications of Oumuamua extend far beyond the immediate question of what that one object was. They reach into fundamental questions about the nature of our galaxy, the prevalence of life, and the very framework within which we conduct astronomical science. Each of these broader implications deserves careful consideration because they shape how we interpret current observations and how we plan future research. Consider first what Oumuamua tells us about the galactic environment. Before 2017, our knowledge of the material between stars came almost entirely from remote observations. We could study distant stars through their light. We could analyze the gas and dust in interstellar clouds through spectroscopy. We could measure the magnetic fields and cosmic ray populations through indirect means, but we had no direct samples of material from outside our solar system. Voyager 1 had crossed into interstellar space in 2012, but it carried no instruments designed to sample physical objects. It could measure the plasma and magnetic field of interstellar space, but it could not capture and analyze any actual matter from beyond. Oumuamua changed this. For the first time, a physical object from another star system passed close enough to be studied. Even though we couldn't sample it directly, we could observe it with unprecedented precision. The light it reflected carried information about its surface composition. Its motion told us about its origin and journey. Its behavior in our solar system showed us how interstellar objects interact with stellar environments. We gained, in essence, a remote sample of material from another star system. What did this remote sample teach us? It taught us that the galaxy contains objects with properties we hadn't expected. The cometary visitor Borisov fit our models reasonably well, but Oumuamua did not. The galaxy contains a diversity of interstellar objects greater than our limited theoretical work had anticipated. This is itself a profound finding. It means our models of planetary system evolution, of small body formation, and of interstellar object production are incomplete. There are processes occurring in other star systems that we have not yet understood. The implications for our understanding of planet formation are particularly interesting. The composition of interstellar objects tells us about the composition of the regions where they formed. Borisov's high carbon monoxide content told us about cold formation regions. Oumuamua's anomalous behavior, if it's natural, tells us about exotic formation environments we haven't fully characterized. As we accumulate more interstellar object detections, we will build up a picture of how planetary systems vary across the galaxy. The variations will inform our understanding of how planetary systems form and evolve under different conditions. There's also a connection to the question of life elsewhere in the universe. Comets are thought to have played important roles in delivering volatile compounds and organic molecules to the early Earth. The chemistry that took place on cometary surfaces and in their comi may have contributed to the development of life on our planet. If similar chemistry occurs on interstellar objects, those objects could potentially distribute organic compounds between star systems. The galaxy might be linked by a slow, ongoing exchange of cometary material that carries the building blocks of life from one planetary system to another. This concept, sometimes called galactic panspermia, has been speculated about for decades. The discovery of interstellar objects gives it a physical basis. We know now that material does travel between star systems. The next question is what kinds of compounds those traveling materials carry. If interstellar objects contain organic molecules, amino acids, or even more complex precursors to life, they could be agents of chemical distribution across the galaxy. Even if the molecules they carry don't directly seed life on the planets they pass, they could enrich the chemical inventory of the systems they encounter. The detection of Borisov's specific composition has begun to address these questions. The carbon and nitrogen chemistry of Borisov was rich and complex, including molecules that could serve as precursors to amino acids. Future interstellar objects will be analyzed for similar compounds. If we find that interstellar objects routinely carry complex organic chemistry, we will need to consider how such material affects planetary chemistry across the galaxy. The implications for the origin and distribution of life would be substantial. There's another dimension to the implications. The Avi-Loeb hypothesis, whether or not it's correct for Oumuamua specifically, has reopened the question of how we should search for evidence of extraterrestrial intelligence. For most of the history of SETI, the search for extraterrestrial intelligence, the focus has been on radio communication. The assumption was that aliens, if they exist, would communicate using technology similar to ours and would broadcast signals across interstellar distances. Decades of searches have failed to find any clear signals, despite increasingly sophisticated detection capabilities. The lack of detected signals has prompted reconsideration of the search strategy. Perhaps aliens don't communicate using radio. Perhaps they communicate using technologies we haven't anticipated. Perhaps they don't communicate at all, having no interest in announcing their existence to the galaxy. Or perhaps they're simply too distant and the signals haven't had time to reach us. The possibility of finding physical evidence of alien technology represents an alternative search strategy. If aliens existed at some point in the history of the galaxy, they might have left artifacts behind. Defunct probes, abandoned space stations, fragments of constructed materials. These artifacts might be detectable if they passed close to us. The search for interstellar objects with unusual properties is therefore connected to the broader search for evidence of intelligence beyond Earth. Oumuamua may not have been artificial, But the question raises whether we are prepared to recognize artificial objects if they do pass through our solar system. The Galileo project that Loeb founded represents one attempt to systematize this kind of search. The project aims to develop dedicated infrastructure for detecting unusual objects and recognizing their nature. Whether the project succeeds in finding any artifacts remains to be seen, but the conceptual shift it represents is significant. We are beginning to consider that physical evidence of intelligence might be more accessible than communicative signals. There's also a philosophical dimension. The case of Oumuamua has forced the scientific community to think carefully about how we evaluate unusual observations. When something doesn't fit our existing categories, what do we do? Do we expand the categories to include new possibilities? Do we propose unusual circumstances that would allow our existing categories to apply? Do we consider unconventional explanations, including ones that touch on speculative possibilities like alien technology? These are not easy questions, and the scientific community continues to work through them. The debate has also exposed tensions within the scientific establishment about which questions deserve serious engagement. Some topics are considered respectable. Studying the composition of comets is respectable. Searching for radio signals from possible aliens is respectable, even if no signals have been found. Proposing that an unusual object might be artificial alien technology is, to some, a step too far. Loeb has been criticized not just for the specific claim, but for crossing what some consider a line of respectability. This tension reflects deep questions about the nature of science. Science is supposed to follow evidence wherever it leads, but it also depends on community norms and shared standards. When evidence points in unconventional directions, scientists must decide whether to follow it. Sometimes the evidence is misleading, and the unconventional direction turns out to be wrong. Other times the evidence is correct, and the community must update its standards. Determining which case applies in any given situation requires judgment. For Oumuamua specifically, the question remains open. The evidence is suggestive but not definitive. The natural explanations are strained but not impossible. The artificial explanation is consistent with the data but requires accepting a remarkable premise. Reasonable scientists can disagree about which is more likely. The debate has played out over years and will probably continue for years more. What we can say with certainty is that Oumuamua has changed how we think about the solar system and the galaxy. It has demonstrated that interstellar objects do exist and do pass through our cosmic neighborhood. It has shown that some of these objects can have profoundly unusual properties. It has motivated investments in better detection capabilities and broader thinking about what we might find. Whatever Oumuamua actually was, its impact on astronomy is undeniable. There's one more dimension of the impact worth considering. Oumuamua has captured public imagination in a way that few astronomical objects have. People who normally don't follow astronomy heard about the strange interstellar visitor. Articles appeared in mainstream media. Documentaries were produced. Books were written. The general public engaged with questions about the nature of the universe and the possibility of life beyond Earth. This public engagement is itself valuable. It connects ordinary people to the work of professional astronomers and helps maintain the social support that science needs to continue. The interest sparked by Oumuamua has also influenced the careers of young researchers. Students who might have pursued other directions in astronomy have been drawn to the field of interstellar object studies. The next generation of astronomers will include people whose interest was kindled by the strange object from another star system. They will bring fresh perspectives to the questions that Oumuamua raised. They may eventually find answers that current researchers cannot. The story of Oumuamua is, in a real sense, just beginning. The brief observation campaign in 2017 and 2018 was only the first chapter. The continuing analysis of the data, the search for similar objects, the development of new instruments and missions, all represent ongoing chapters in a story that will unfold over decades. The questions raised by that single object will continue to drive research for a long time to come. For now, we should turn to the practical question of what we should do next. What are the most important investigations to pursue? What instruments should we build? What missions should we plan? How should we organize the international effort to study interstellar visitors? The most immediate priority is improving detection capabilities. The Vera Rubin Observatory has just begun its main survey operations and should detect new interstellar objects regularly. Other survey telescopes are being designed or upgraded. The Pan-SDARS system continues to operate. The Atlas network has expanded. Each of these contributes to the overall detection capability. The combined network should ensure that we catch most interstellar objects passing close enough to be studied. Beyond detection, we need rapid response capabilities. When an interstellar object is detected, we need to be able to mobilize observations quickly. Coordination among observatories has improved since Oumuamua's brief visit, but more can be done. The future of interstellar object exploration requires not just better detection, but better study. Comet Interceptor remains the most concrete plan for actually visiting an interstellar object with a spacecraft. The mission concept involves launching the spacecraft to a stable orbit point between Earth and the Sun, where it will wait until a suitable target is identified. When an interstellar object or pristine long-period comet is detected, the spacecraft will use its onboard propulsion to maneuver into an intercept trajectory. The encounter will be brief, perhaps lasting only minutes during the actual flyby, but the data collected during those minutes could exceed everything we know about all interstellar objects combined. The instruments aboard Comet Interceptor are being designed to maximize the science return from a brief encounter. Cameras will provide direct imaging at resolutions impossible from Earth-based observations. Spectrometers will measure composition through reflected sunlight and through any released gases. A magnetometer will detect any magnetic field the object might carry. Dust analyzers will catch any particles released by the object and determine their composition. A plasma instrument will measure the interaction between the object and the solar wind. If a Oumuamua-like object is detected and the spacecraft can be redirected to intercept it, the resulting observations could finally resolve the mystery. Direct imaging could determine the shape definitively, settling the debate between cigar and pancake geometries. Spectroscopic measurements with the instruments close to the object could detect any compounds being released, even hydrogen, which is essentially invisible to remote observations. Direct sampling, if it occurs through dust collected by the spacecraft, could provide the first physical material from another star system to be analyzed. The challenges are substantial. Comet Interceptor will only have a single chance to make its encounter. The interstellar object's trajectory will need to be calculated precisely enough that the spacecraft can be sent to the right place at the right time. The relative velocities will be enormous, making the encounter geometry critical. The spacecraft has limited propulsion capability, so the orbital geometry must allow an intercept with the fuel available. Many possible targets will be impossible to reach. Only certain trajectories will result in successful encounters. Beyond Comet Interceptor, more ambitious missions are being proposed for the longer term. NASA has studied concepts for a dedicated interstellar object mission that could rendezvous with rather than just fly past its target. Such a mission would require much more powerful propulsion than chemical rockets can provide. Solar sails, electric propulsion, and even nuclear options have been considered. The technology development required is substantial, but the science return would be correspondingly greater. A rendezvous mission could study an interstellar object over weeks or months, providing comprehensive characterization that no flyby could match. There are also proposals for missions that would carry samples back to Earth. If a spacecraft could collect material from an interstellar object and return it to Earth, the analysis possibilities would be transformative. Modern laboratory techniques can determine compositions at extraordinary levels of detail. We could measure isotope ratios with precision impossible from remote observations. We could conduct microscopic examinations of individual grains. We could test for biological precursors with sensitivity far beyond any onboard instrument. A returned sample from an interstellar object would be among the most valuable scientific specimens ever obtained. The technological requirements for sample return are even more demanding than rendezvous. The spacecraft would need to match velocities with the target precisely enough to collect material safely. It would need to maintain its trajectory while making the collection. It would need to return to Earth on a trajectory that allows safe recovery of the samples. Each step adds complexity and cost, but the potential rewards justify the investment. If we can someday return material from another star system, we will have crossed a fundamental boundary in human exploration. In the nearer term, our understanding will grow through accumulated remote observations of interstellar objects detected by improved survey telescopes. As the sample size grows from 3 objects to dozens or hundreds, statistical analysis becomes possible. We can begin to characterize the population properly, understanding the relative frequencies of different types of objects, the typical compositions, the typical shapes, the typical behaviors. The strange case of Oumuamua will be placed in context, either as a representative of a recognized class or as a genuine statistical outlier. The data accumulated from many interstellar objects will also constrain our models of how planetary systems eject material. We will learn what kinds of bodies are most commonly ejected, which compositions are favored, what timescales are involved. This will feed back into our understanding of planet formation generally. The galaxy will become better understood as a place where material flows between star systems through the slow drift of ejected bodies. For the public, the continuing story of interstellar objects offers an ongoing connection to fundamental questions about our place in the universe. Each new detection becomes a moment of public engagement. News articles appear. People ask questions. The wonder of discovery is renewed. This is valuable in itself, regardless of the specific scientific findings. The cultural impact of interstellar object exploration is part of its overall value. Now we should return to the central question that motivated this exploration. What was Oumuamua? Looking at everything we've discussed, can we reach a final answer? The honest response is that we still cannot. The evidence is suggestive but not conclusive. The natural hypotheses can be made to fit with sufficient creativity. The artificial hypothesis cannot be ruled out with current data. The mystery remains. What we can say with confidence is that Oumuamua was profoundly unusual. Whatever its true nature, it does not fit comfortably within our existing categories. It forced us to expand our thinking about what interstellar objects might be. It demonstrated that the universe contains things we don't yet understand. It reminded us, as the Voyager missions have also reminded us, that our models of the cosmos are always provisional. New observations can always reveal aspects of reality that our theories haven't anticipated. This humility is, in some ways, the most important lesson of Oumuamua. We are not all-knowing. We are not even close to all-knowing. The universe is far stranger and more complex than our most sophisticated models suggest. Every act of careful observation has the potential to reveal something unexpected. The history of astronomy is, in large part, a history of being surprised by what we find when we look more carefully. The same is true for the Voyager mission discoveries discussed in the source material for this script. Those spacecraft were sent to study Jupiter and Saturn, and they discovered that even the boundaries of our own solar system were not where we thought they were and not shaped as we expected. The interstellar medium did not match predictions. The galactic magnetic field surprised us. Cosmic ray distributions were not what we anticipated. Every observation revealed something new. The pattern repeats. We make predictions based on our best theories. We design instruments to test those predictions. We send the instruments to do their work, and what they discover is almost always different from what we expected. Sometimes the differences are small refinements. Other times they are profound revelations. In all cases, the universe teaches us that we do not understand it as well as we thought we did. Oumuamua fits into this larger pattern. It was an object we had been predicting for decades. We thought we knew roughly what to expect when one was finally detected. We were wrong. The object that arrived defied our expectations in multiple ways. Even after years of analysis, we still cannot say definitively what it was. The mystery persists because the universe is more complex than our models. For those who find this unsatisfying, who want a clear answer to the question of what Oumuamua was, I can offer only this. Sometimes the most important scientific discoveries are not specific answers, but recognition of new questions. Oumuamua may have been a hydrogen iceberg with unusual composition. It may have been a nitrogen fragment from a disrupted planet. It may have been a defunct piece of alien technology. It may have been something none of us have yet imagined. The point is that we don't know, and that not knowing has driven and will continue to drive scientific investigation in productive directions. The exploration of our solar system continues. The Voyager spacecraft, still operating in 2026 despite being designed for 5-year missions, continue to teach us about the boundary of solar influence. New missions are being planned to explore the heliosphere more thoroughly. Comet Interceptor will be launched in the late 2020s, waiting for a target. The Vera Rubin Observatory is detecting unusual objects nightly. The James Webb Space Telescope is characterizing distant objects with unprecedented detail. Future telescopes and missions will further extend our reach. Each of these activities is, in its own way, an act of exploration. Each one tests our understanding against reality. Each one offers the potential for surprises. The mystery of Oumuamua, while specific to one object, is part of a larger pattern of inquiry that defines the entire enterprise of scientific exploration. We look outward, we measure carefully, we test our predictions, and we learn that the universe is always more interesting than we knew. The two Voyager spacecraft, drifting outward through interstellar space, carry their golden records as messages to anyone who might find them. Oumuamua, racing back into interstellar space after its brief visit, carries no message that we can read, but it has left its own mark on human understanding. It has shown us that interstellar objects are real, that they can be strange, and that we still have much to learn about even the most basic features of our cosmic neighborhood. In the distant future, perhaps thousands of years from now, perhaps millions, the descendants of humanity may know what Oumuamua was. They may have visited it directly. They may have found other examples and understood the population. They may have spread to other star systems and seen interstellar objects from a different perspective. Whatever they know, they will know it because of the work that began in 2017 when a small spot of light moved across the field of view of a telescope on a Hawaiian volcano. That work continues today, and it will continue for generations to come. The mystery of Oumuamua may eventually be solved, or it may join the small set of historical curiosities that science never definitively explains. Either way, the object will have served its purpose. It will have reminded us that the universe is bigger and stranger than we know, that exploration always has the capacity to surprise, and that even passing visitors can change how we understand our place in the cosmos. Two spacecraft from Earth continue to drift outward. A small object from another star drifts outward in a different direction. The galaxy moves silently around them all, hundreds of billions of stars going about their slow business while the small bodies pass between them. Somewhere out there, perhaps, other civilizations watch their own night skis and wonder what mysteries they might encounter. We may never know if they exist, but because of Oumuamua and the questions it raised, we will be looking. We will be ready. And the next time something strange passes through our cosmic neighborhood, we will see it sooner, study it longer, and perhaps finally understand what visits us from the spaces between the stars.